So here we're briefly going to describe the process of nucleosynthesis and something called the Otto-Harkins rule using this diagram here by Anders and Graves. Now what they've done here is they show the abundance of elements. So here's the abundance moving upwards on the diagram relative to atomic number, which is increasing to the right. These are nominally the abundances of elements in the solar system, but the solar system by mass is dominated by the sun. So these are effectively solar abundances. But they would be the same if you took the entire solar system and wrapped it into a ball and then analyzed the whole thing. Hydrogen is the most abundant element, so here it is at the top of the chart, and then helium is the next most abundant. Now, where do these elements come from? Well, we'd have to go back to the early parts of the Big Bang. In the first few minutes of the Big Bang, you could take protons. So proton has an atomic number of 1 and an atomic weight of 1. And we can add to that a neutron, which has an atomic number of 0. Remember, the atomic number is just telling us the number of protons. So by definition, a proton has an atomic number of 1. A neutron has an atomic weight equal to that of a proton, so it's also going to have an atomic weight of 1. And if we add these two things together, then we can have a hydrogen atom. Now, this is not any kind of hydrogen. It's got an atomic number of 1, but an atomic mass of 2. And this is often written as D because we call these are the very same thing. This guy here is equal to this, and we call this deuterium. Give it a special name. It's really the same element chemically. It's going to act like hydrogen, but it's got twice the atomic weight of typical hydrogen, which has an atomic weight of just 1. And we can take this deuterium atom, or we can write hydrogen with an atomic number of 1, or we can write the D. It really doesn't matter for our purposes here. We could take two of these fellows. Once we've made this stuff by combining protons and neutrons, we could take the products, this hydrogen or deuterium stuff, and when we add it together, we get helium-4. So 2 plus 2 gives us an atomic weight of 4. And then down here, the number of protons, 1 plus 1 gives us 2. Plus, there's a whole lot of energy that comes off. That's true for this equation over here, and then this equation that we've written here. So this happens in the Big Bang in the first few minutes. Now, this means that most of the universe is going to be dominated by hydrogen and helium. And when we see these very high concentrations over here, most of these elements, most of these atoms of hydrogen and helium were created in the Big Bang during those first few minutes before the sun even formed. So this is the stuff that the sun formed from. Now, once the sun forms and other stars form, we start creating the rest of these elements here. Now, another important aspect of this is this zigzag pattern. All of these fellows here, carbon, oxygen, neon, iron, etc., they tend to have an even number of protons and neutrons. And these fellows down here, scandium, vanadium, potassium, chlorine, etc., they tend to have an odd number of protons and neutrons. So you could see the elements that have even numbers of protons and neutrons tend to be more abundant than those that have an odd number. Now that's going to be very important to us when we start looking at rare earth element diagrams. So we're going to go a little bit further into nucleosynthesis and talk about why these even numbered elements are favored. So let's go ahead and erase the chalkboard. So we have stars that form maybe a billion or so years after the Big Bang, and then inside of stars we could take something like deuterium with its atomic weight of 2 and atomic number of 1. Remember, that's the same as a hydrogen atom with an atomic weight of 2. And we can add that to another proton, and when we do that, we get helium-3. So this is helium. It's got 2 protons in the nucleus, otherwise it would not be helium. It's got 1 neutron that's being donated from that deuterium atom, and so we get helium-3. And then we're going to ignore this for the rest of our equations that we're going to write. But there's a whole lot of energy that's produced as well, related to the E equals mc squared, mass being converted to energy by Einstein's equation. So then we can take some helium-3 that's created, We're going to ignore the subscripts now. Anytime we write helium, then by definition we have to have a subscript of 2. But once we write helium, then that subscript is really defined. So we just leave it off. So if we take 2 helium atoms that are formed by that process, we can combine them to make helium-4 and 2 hydrogen atoms that would be released in the process. So this is an interesting sort of creation and decay process. We start out with helium, 2 helium atoms. We end up with 1 helium and 2 hydrogen atoms. And then those helium atoms, helium-3 that's not been completely reacted, can react with this newly created helium-4, and we can make something like beryllium-7. The beryllium-7 can react with something like hydrogen to give us boron with an atomic weight of 8, and then the boron with that atomic number of 8 can decay into something like beryllium with an atomic number of 8 plus an electron, but not really an electron, an electron type particle that has a positive charge. This would be called a positron. It is the antiparticle of an electron. If a positron meets an electron, they will combine and release pure energy. Now, this is where the fun starts. We can take that beryllium-8 and it will possibly decay. It's actually quite likely to decay into 2 helium-4 atoms. So take a look at this. We started out by creating helium-4 up here by combining helium-3 from deuterium and protons, and we went through this process of creating beryllium and then boron, and then another isotope of beryllium, and now we're back here with more helium. So we're back over here, not quite at the starting point, but in an early part of the phase of building up these elements. So what we're doing is we're creating these other elements like beryllium and boron, but then they're just being consumed in these other reactions. They won't necessarily be completely consumed. We'll have some boron and beryllium left, but they're going to be in lower abundances because they are also being consumed and creating more helium. And then what does that helium do? Well, we can take 3 helium atoms, so helium-4 plus helium-4 plus helium-4, and if we have very, very high temperatures and very, very high density at the center of the star, they can combine in the so-called triple alpha process to give us carbon-12. So if we come back to the diagram, you can rewind it to see the figure, you'll see that things like carbon-12 and oxygen-16 and neon-20 are all in very high abundances. And why is that? Well, for the case of carbon-12, we're simply taking 4 helium atoms to make that. Not 4, 3 helium atoms. I'm jumping ahead of myself. We have 4 helium atoms coming together to give us oxygen, and then we can have 5 helium atoms that come together to give neon. And then you can imagine a lot of other kinds of reactions that involved each of these fellows, carbon, oxygen, and neon, and also helium and hydrogen, to get us all of the elements up to iron 56. Iron 56 forms something of a peak. We cannot create anything by fusion beyond iron 56. So this whole process here, this is a process called fusion, where we're fusing these elements together to form carbon. All the other reactions we've shown prior to this are also fusion reactions, where we're fusing beryllium and hydrogen and deuterium, etc., to make these heavier elements. The process stops at iron 56. When we fuse these elements, as I said before, we're getting energy out of that system. At iron 56, we no longer get any energy out of that system, so the system is no longer self-sustaining. You have to put energy in to fuse elements that are heavier than iron. And so inside of a star, since we no longer have any energy once we get to iron 56, then the star no longer continues the fusion process. the whole process of nucleosynthesis breaks down, and the star is going to change its form, turn into a red giant, and that's something for a different discussion. Now, when we say a peak, this is a peak in atomic number, but it's actually a minimum when it comes to energy. So if you took a look at the amount of energy that you get, you'd get a lot of energy from fusing hydrogen, a little bit less from fusing helium, a little bit less from fusing carbon, and the energy would decrease all the way down to iron 56. And at this point, when we're making iron 56, we just get a tiny little bit of energy out of the system. And if we try to fuse iron 56 with anything else and create heavier elements, then there's no energy that we get at all out of that. In fact, you have to put energy on the other side of the equation. You have to put energy into the system. So energy plus iron 56 plus other elements would be required to get the heavier elements. So we create elements heavier than iron by other processes, which we are going to save for another video. But the key thing here is because we're adding helium atoms together, so-called alpha particles. Remember, helium nucleus is an alpha particle. It has an atomic weight of 4 and an atomic number of 2. When we start fusing these guys together, we do so in ways that we tend to create things that have even numbers. Now, we create a lot of stuff with odd numbers. We looked at how we can create beryllium-7, but those end up being either created not at the same rate or created then consumed in other reactions. And so we have less of elements that have odd numbers and higher abundances of elements that have even atomic weights and atomic numbers. And that's going to come back to be very important when we look at rare earth element diagrams, the kind of chondrite normalization that we'll talk about later, when we start plotting elements on logarithmic charts and comparing abundances.